Okay. So the main task that we're asked with for graphing a rational function, I'm going to say the main task, one of the primary tasks, is to find asymptotes. Okay. Asymptotes, by what you know them to be, are lines that we cannot cross in our graph, right? Okay. They set kind of a line of demarcation in which you cannot have a graph being drawn at those spots. Okay. Basically, they're visuals for telling you this is a problem algebraically for the domain of your function. Okay. You don't have any points plotted on asymptotes. Okay. Now that's the way we understand asymptotes, but that's not always the case when we talk about horizontal asymptotes. When you have vertical asymptotes, that is absolutely 100% always true. When you have horizontal asymptotes, which we will, you may cross them. And I'll show you the algebra that will determine whether we do or we don't. Okay. This statement here, okay, basically tells us how we determine what our horizontal asymptotes are. Okay. It says in general, if your rational function is p of x divided by q of x, so two polynomials being divided by one another, okay, and they have the same degree, and all we have to do is look at the leading coefficient of p and leading the coefficient of q, divide them, and that's our horizontal asymptote. Okay. What I want to do here is just kind of show you why that's the case. Okay. And to be honest with you, as we work through this, we're going to talk about three different cases, three different situations in which we can realize what our asymptote is. All right, so I'm going to say my R of x is equal to, let's just say, 3x to the third plus 4x squared plus 5. And let's say my denominator here, which would be this q that they're talking about, q of x, let's say that is 4x cubed plus 7x squared minus, say, 3. Okay? Does not matter what those are. Okay? Doesn't matter how many terms we have there, because I'm only interested in finding my horizontal asymptote right now. And if you guys remember what we did with polynomials, when I just had that blue polynomial, and I was interested in finding the end behavior. That's what horizontal asymptotes are doing for us. They're finding end behavior. Okay? We would look at just the leading degrees, right? Or the leading term, and that would tell us our end behavior. So the same thing should apply here, but since I have two of them being compared through division, I'm just going to look at the two leading terms and compare them through division. I want to explain why this works. Okay? When we take a 3x cubed out of everything in the numerator, we did this once, right? If I take a 3x cubed out of everything, and I could just rewrite it this way: 3x cubed over 3x cubed, plus then it'd be 4x squared over 3x cubed, plus then 5 over 3x cubed, right? That's what that numerator would turn into. Now, is that going to reduce? What's that going to turn into right there? It's going to turn into a 1. Okay. This is going to turn into a 4 over 3x. 4 over 3x. And this is going to just stay as 5 divided by 3x cubed, right? No cancellation there. Now I'm going to do the same thing for the denominator. But I'm going to take a 4x cubed out. Okay? So it's going to be 4x cubed over 4x cubed. That's going to give me 7x squared over 4x cubed. And it's going to give me a minus 3 over 4x cubed. What is that term going to turn into? 1. Okay. What's that going to turn into? 7 over 4x. And that one doesn't reduce, right? Now, I told you we're interested in behavior, right? We're interested in when x gets really, 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 really big in the positive direction or really, 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 really big in the negative direction. Well, if x is really, really, really big in either of those directions, what does 4 divided by 3 times a really, really, really big number look like? Or what do you get close to? That goes to 0, right? Does this go to 0 as well for the same reason? This happens actually a lot faster there. Okay? What's this going to go to? 0. What's that going to go to? 0. So what do you have in that set of parentheses? Just 1. What do you have in this set of parentheses? Just 1. So what are you left with? Essentially just the what of our original, just the leading degree or leading terms of our original function, right? Okay. Now, once we have those, okay, here it says both have the same leading degree. Okay, they're both the nth degree here. What's going to happen with the x to the third over x to the third? What are they going to do? They're going to cancel as well, and you're going to be left with just 3/4. There is your end behavior. As x gets really, 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 really big. Okay, and you could try this. You could take this original r of x and plug in like x to be 1,000, and x to be 10,000, x to be 1,000,000. And you're going to see if that number gets closer and closer and closer to 0.75. It'll never get there. It'll get very close to it. Does that make sense? Okay. So that's my end behavior. But that was when my leading terms had the same exponent. Okay. Let's kind of mess around a little bit with this and say, what if this leading term here in the top, 3x, what's the third? Let's write it as 3x squared now. All that factoring and giving me that set of parentheses of 1 plus 0 plus 0 plus however many zeros I need in there, it's still going to be the same. Okay? So it's still eventually, when x gets really, really, really big in either direction, it's still going to give me the comparison of the leading terms. Does that make sense? Okay? What's going to happen there? You're left with 3 over 4x. Okay? Now, that's a variable expression. We have to understand what that's telling us. That's telling us as x gets really, 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 really big, what's 3 divided by a really, 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 really big number? Yeah. As x goes to infinity, plus or minus, this thing is going to 0. There's my horizontal asymptote. When I do that leading comparison, okay, of the leading terms, and I'm left with a variable in the bottom, I'm always left in with a horizontal asymptote of y equals 0. Okay? Now the messy one, and we'll get to this later in the week, we got time. The messy one is like when this is, let's say, to like the 5th power. So now we have 3x to the 5th over 4x cubed. Now where's the variable left? Up top, right? So it's going to leave me with 3x squared over 4. Okay? Now think about what happens when x gets really, I'll just kind of draw a rough sketch here. When x gets really, really, really big in the positive direction, you get a positive number, a very large positive number divided by 4. Isn't that still a large positive number? As x goes to the right, your y's are going to positive infinity. Now, as x goes to the left, a very, very large negative number, square it, becomes 3 times a very large positive number. A very large positive number divided by 4 is still just a very large positive number, right? So there's kind of my end behavior. When the leading degrees are different and the numerator is bigger, we actually get, we call that, it's not a horizontal asymptote anymore. It's called an oblique asymptote. And in this case, the asymptote would actually be a parabola. Okay? That's the problem because when these differ, however these differ, they differ by 1 degree, your asymptote, your oblique asymptote will be linear. If they differ by 2, your asymptote will be parabolic. If they differ by 3, your asymptote will be cubic. Does that kind of make sense? And then in finding that asymptote that is maybe a cubic asymptote is going to take us back into the early parts of chapter 3 where we learned how to graph cubics and get all that process with factoring and all that kind of stuff. So it does get messy when we look at oblique asymptotes. For the most part, we'll talk about linear ones, okay? When they differ by 1 degree. And a lot of times when they're called linear, a lot of times they call them slant asymptotes. But oblique is kind of the word that we just use to encompass all of them, right? Okay. Like polynomial is the word that we use to encompass all polynomials, but we then have special ones called monomials and binomials and that kind of stuff, right? So this slide right here kind of explains that. Okay, explains those three situations. And part two, it says if n is less than m, okay, so n is the numerator exponent, m is the denominator. I know it's zoomed out real far, hard to see. Okay, so if that one, if n is less than m, the cancellation is going to occur, so you always have an x in the bottom. Might be x to the first, might be x squared, might be x to the third. You're just left with more x's in the bottom than you were on the top. And what that means is when x gets really, really big, you have 1 divided by, or 2 divided by, or 3 divided by a really, 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 really big number, which is always going to get you to y equals 0. Okay? So when your leading degrees differ that way, you're always getting a result of y equals 0 as your horizontal axis. When they're the same, when the leading degrees are the same, okay, the variable components kind of cancel off completely, and all you're left is the leading coefficient divided by the leading coefficient. So that's what your asymptote's going to be. Okay? And the third one is kind of vague. It doesn't get into, because we could probably devote kind of a whole section or maybe even a handful of sections to dealing with that third kind of bullet down here where it says n is greater than m and r has no horizontal asymptote. If it doesn't have a horizontal asymptote, it's got to have something. It's got to have a slant asymptote, or like I said, we call them oblique asymptotes, just kind of in general. And those can be asymptotes that are lines. They could be quadratic or parabolic. They could be cubic, whatever. Okay. Like I said, for the most part, we're going to try to deal with, when we do talk about slant asymptotes, talk about linear ones. Okay. The first object here says the vertical asymptotes of R are the lines x equals a, where a is a 0 of the denominator. Think about this. When we look at a rational function, we can never divide by what? 0. Okay. Dividing by 0 always gives us a problem. Okay. So in our graphs, the visual cue to remind us that we have a problem with division is a vertical asymptote. Okay. So if you go back to like chapter 1 and chapter 2 earlier in the year, we spent some time with looking at rational equations, saying, where are my problems? Where are my domain issues? The reason we did that is because now it's just taking that information and reusing it here. Okay? You should be able to look at a rational function, automatically know, oh, I can't divide by 0. That's where I have an issue with my graph. And we move on finding our vertical asymptotes more than that. Is that all right? Okay. Once we do that, there are some kind of rules that we need to abide by. Okay. The first thing I always do, guys, is, and I'll put this up for you. There are some rules within this PowerPoint. I think they're kind of vague sometimes. This is under section 3.6 on my website. You guys can print that out. You can write down your notes, whatever. The steps for graphing a rational function. Okay. First thing is the fact of the numerator, fact of the denominator. Okay. Now at this point in our algebra careers, when I say factor, that encompasses a lot of things, right? Quadratic things, cubic things, quartic, using P over Q, that kind of stuff. Okay. Everything we've talked about this year has kind of led up to being able to graph rational functions so far. Okay. Something we didn't talk about so far is when we have common factors. You might factor the numerator, you might factor the denominator, and there might be like an x plus 1 up top and x plus 1 on the bottom. Well, those cancel each other out, right? If they cancel each other out, you no longer have a vertical asymptote x plus 1. Okay? You actually have what we call a hole, okay? Or a point discontinuity. Okay? A little bit easier to call it a hole. But basically what we do is we then take and try to figure out the location of that hole. And that's the thing about your technology. If you were to graph these on K384, Desmos, GeoGebra, they're not going to tell you the locations of the hole. They're not going to put an open dot on your graph. So we have to do the algebra to find it. So we'll talk about that. We don't see that today yet. We'll get there at some point in the next couple days. Number 3 says factors less than the denominator are set equal to 0. You set your denominator equal to 0, and that's always going to give you your vertical asymptote, because that's your place for dividing by 0, right? And that's where we have issues. Okay. The 4th one says comparison of the leading terms in the numerator and denominator. That's going to give you your horizontal asymptote. I just kind of walk through with those 3 kind of bullet points for different types of leading terms you could have and how they compare with their exponents. Okay. Step 5 says set your horizontal or oblique asymptotes to equal r of x, which is your original function, and see if you cross the asymptotes. Okay. Because when we talk about, and this is why I think horizontal asymptote is kind of a bad name for it, because we think vertical asymptotes, we understand vertical asymptotes, we're never allowed to touch them, right? Never allowed to cross them. Horizontal asymptotes are only an in-behavior concept, so you can cross them. Okay, you just won't cross them at a billion, or you might. Okay, if you, I don't want to say that. You can cross them, but you cross them relatively close to 0. Okay, now what's relative mean? Okay, well, it could be a billion. Depending on how far out on the x-axis I want to go, a billion could be pretty small, right? If I go out to a googolplex on the x-axis, a billion is small. Okay, so those are kind of things to kind of think about. You can cross the horizontal asymptote. You need to burn that into your mind because it's something we have to check every single time that we have one of these things. And we're going to see it twice today. The next thing says set reduced numerator factors equal to 0 to find x-intercepts. That's an easy concept. You guys know how to do that. I'll show you why that works here in a little bit. But we got to find our x-intercepts. That's when y is equal to 0. Okay. We then have to find our y-intercepts. Well, that's when x is set to 0, right? Okay. So those 2 things, step 6 and 7, are things that we've done a lot in the past, all the way back to chapter 1 in algebra 1. Okay. Number 5, that's just using old algebra. Okay. That's a system of equations essentially. You guys know how to solve it. Okay. So everything that we're doing within these 8 steps are pieces of algebra that we've used over and over and over again since we were maybe in the 8th or 9th grade. Okay, we're just now putting together, structuring them in a meaningful way. So well done. A couple examples here today, guys. And kind of give them to you in multiple versions. So what this one says, and it just said find the asymptotes, but I want to go through the entire process. I'm going to give myself a little bit of room here because there is a lot of work that's involved. On your test, it will ask you for supporting work. Okay, so we're going to need that, and just understand that telling me because you graphed it on your TIA 384 and you're able to recognize, well, here's an asymptote here, here's an asymptote here, and just writing that information out is not going to be enough to get you credit. Does that make sense? Okay, you have to use the algebra, the supporting work to garner that credit. All right, so what I always do, guys, is I write a list of things that I'm always looking for. Okay, so I'm always going to be looking for vertical asymptote. I'm going to be looking for a hole. Okay, and those 2 things, they kind of tie together. Okay, so we'll pay attention to that kind of stuff. We're then going to look for our horizontal asymptote. Or asymptote, we don't have one of those. We're going to ask, do we cross it? Okay. We're then going to find our x-intercepts, our y-intercepts, and then we'll do a t-chart if necessary. And all of this information, guys, is being collected in the effort of graphing. Okay? So once we get all this stuff, we're going to take all that information, we're going to go over to GeoGebra and see if that stuff mimics our graph, okay, or it helps us develop our graph. All right, so the number one thing that you want to do is to factor the entire numerator and factor the entire denominator, okay? Now, you can start to realize and understand that, you know, the higher those degrees, the elongated that process is, right? Okay, if that's a 5th-degree polynomial at the top and a 6th-degree polynomial at the bottom, and that might be a 15-minute process just to get this thing factored. It is what it is, okay? We're going to have to use all of our tools for factoring to do this. So this one here, when you look at that, what technique are you going to use to factor the top and the bottom? AC method, okay? So top is going to give you, we take A times C, and top is going to give you -3, right? What two numbers multiply together to give you -3, but add up to give me -2? -3 and 1, good, okay? So we're going to write the top as 3x squared minus 3x plus 1x minus 1. While I'm at it, guys, I like to do it this way. You kind of have to see what your preference is. I'm going to now do the same AC stuff for the bottom. I'm just going to kind of do the same thing over and over for top, and then do it to the bottom. And do it to the top, and then do the bottom. Top, and then bottom. Does that make sense, everybody? Okay. So now what would be the AC method here? What number am I looking for here? Okay, so I'm looking for -4, so it would be -1 and 4, right? Those two numbers that multiply together give me -4, and have to give me +3. So we're at the bottom, that's 2x squared minus 1x plus 4x minus 2. Now we'll group. Okay, so when I group the top, will come out of the front 2. 3x, leaving me x minus 1, right? We'll come out of the back 2, 1. On the bottom, we'll come out of the front 2, just an x, and it leaves me 2x minus 1. We'll come out of the back 2, 2, and leaves me 2x minus 1. So now, is everybody good with the stuff in the red? Can you rate the stuff in the red? So now what this thing here would look like is 3x plus 1 times x minus 1 over x plus 2 times 2x minus 1. Is everybody okay with what's in that box? Can you rate that? All right, so we've effectively factored top and bottom, right? That took some time. Now, if we're not walking and talking through it, maybe it's a little bit quicker. But you can understand that if it's a 3rd degree, 4th degree, 5th degree, that's going to be a very time-consuming process. Okay. All right. So vertical asymptotes and holes, they come together, and really what you want to do is see if you have any holes first. Holes show up where we have factors in the top and the bottom that are going to cancel each other out. Okay. Do I have any of that? No. Okay. So in this case, holes are not applicable. We don't have them existing. Okay. The vertical asymptotes, okay, remember vertical asymptotes are a visual cue for us to tell us that we do not have a domain value because of division by 0, right? So what I'm going to do is I'm going to take my denominators, okay? My denominator is equal to 0 is going to give me my vertical asymptote. So if I say x plus 2 is equal to 0, doesn't that give me x equals -2? And if I take 2x minus 1 equal to 0, doesn't it give me x equals 1/2? These are equations of vertical lines that are vertical asymptotes. Is that all right? Okay. Horizontal asymptotes. Okay. And this is one of the things that, you know, even though we gain a lot of information from the factored version of our function, The expanded version still has its uses, still has its benefits. Okay? I want to compare my leading degrees, right? Make sure they're in descending order. Make sure both P of X and Q of X, the numerator and denominator, are in descending order, and then compare them. Okay? What I always do, I don't like remembering those 3 rules that I gave you at the beginning. I like to just compare them and just come over to the side and do the division. If I did the division, what am I left with? Left with the x squared. Cancel, you're just left with 3 halves, right? So there's my asymptote. Y equals 3 halves. If I did my division, I was left with 3 over like 2x. I still have a variable left over. Understand what the asymptote is. It's in behavior, so x gets really, really big. So see what happens if I were left with like 3 over 2x. Okay, x gets really, really, really big. What's 3 divided by a really, really big number? Yeah, be 0, right? Okay. If you really think about it, this is just a transformation of 1 over x, which had that asymptote of y equals 0, right? Okay. So that's another kind of connection that we can make to realize why, when we have a variable in the denominator, our asymptote is always y equals 0. Okay. The part that I think is something people overlook, they struggle with, is finding the horizontal asymptote and whether we cross it or not. Okay. Here's the idea. Okay. If you remember back to Algebra 1, you talked about how you find whether 2 graphs cross each other, whether 2 equations are ever the same. Okay. And doing that, the terminology used was system of equations, right? You have, right now, y equals 3x squared minus 2x minus 1 over 2x squared plus 3x minus 2. You also have the horizontal asymptote of y equals 3 halves. Right? Does that make sense? Well, if these 2 things are going to cross, then their x values are going to be identical and their y values are going to be identical, right? So if their y's are going to be the same, that means that and that are going to be the same value, right? Can I replace one of those with the other? Can I take this y out and replace it with 3 halves? That make sense to everybody? Okay. So setting your horizontal asymptote equal to your original r of x is going to allow you to see if you cross it. Here's the thing. You then have to understand, what does that produce? What kind of algebra is present now? I have a ratio equal to a ratio. What do you do when you got a ratio equal to your ratio? You cross multiply, right? Okay. It's ultimately the same thing. It's a special case scenario multiplied by an LCD. Okay. Your LCD here would be 2 and 2x squared plus 3x minus 2, right? You multiply the left-hand side by 2x squared plus 3x minus 2. You multiply the right-hand side by 2. That's effectively the same thing as cross-multiplying here. Okay? We multiply by that LCD or cross-multiply. And when we do that, I'll just do, you guys remember what those 2 were called back in geometry? What those 2 positions in our proportion was called? Those are our means. Okay? So I'll multiply my mean. It gives me 6x squared minus 4x minus 2. And now, if those are our means, does anybody remember what these 2 are called? Extremes. Good. Okay? So I cross multiply those, it gives me 6x squared plus 9x minus 6. The reason I use that terminology, if you were to look somewhere, maybe you Google and you're confused about the steps, something like that, or how I find whether I cross the horizontal asymptote, they might not say cross multiply. They might say multiply your extremes, multiply your means. Well, that's effectively saying the exact same thing. Okay. What happens with your 6x squared? Cancel, right? All right. Now you're left with something that you can solve for x. When you're left with something you can solve for x, that means you're going to cross your asymptote. If I go ahead and add 4x, I get 13x's over here. I'll add 6 to both sides and get 4. So now x equals 4 13. Does that make sense? Okay. So we do cross our horizontal asymptote at x equals 413. If I'm crossing, because I want the point of crossing, point of intersection. If x is 413, what's y if I'm crossing the horizontal asymptote? 3x. All right. So that's the work that we're going to use every single time to check if we cross the horizontal asymptote. Okay. Now, like I said, we got down to where we can solve for x, right? If you get down to a point where you get something like this, like 2x plus 3 equals 2x plus 7. The 2x is going to cancel, right? It leaves you with 3 equals 7. Does that make any sense at all? That's a false statement, right? When you get a false statement like that, that's enough to tell you you do not cross. Okay? But if you're left with an x, you're going to cross it. Okay? Now you could essentially, depending on how things work out, you could be left with an x squared. You could be left with x cubed and that kind of stuff. So you might have multiple places where you cross your horizontal asymptote. For the most part, what we're going to see is crossing it once, but it could happen where you cross it multiple times, depending on what that multiplication process kind of turns out to be. And I would think that would probably happen most often with maybe oblique asymptotes. All right, so now I got to find x-intercepts. X-intercepts, go back to algebra 1, are when what coordinate is 0? Which when your y-coordinate is 0. So I'm going to take my polynomial, my rational function, my polynomial at the top, polynomial at the bottom, and I'm going to set them equal to 0. We have 3x plus 1, x minus 1, over x plus 2, 2x minus 1. Okay? All of your x-intercept work is easier in the factored form. Okay? Vertical asymptotes, best to use the factored form. The holes, best to use the factored form. Horizontal asymptote, I think the expanded form is best. Cross the horizontal asymptote, I would think that the expanded version is best. X-intercept, the factored version is best. Okay, so you got to kind of understand which format of RX is best to gain this information from. If it's the case, okay, now my denominator for 0 can be anything it wants to be. Okay, I'm going to cross multiply, right? Does that make sense? Or multiply by an LCD. But what happens to x plus 2 times 2x minus 1 when I cross multiply? They go away, right? Okay. So what is the only thing you're left with? You're only left with the numerator equal to 0, right? So a lot of textbooks will talk to you, they'll give you a rule set numerator equal to 0, and that's how you find your x-intercept. Well, why? Why does that make sense? It's a shortcut. Because every single time that you try to find the x-intercept, it's when y is equal to 0. If it's a fraction, you're always going to multiply by LCD, and that denominator always goes away. Does that make sense? Okay. So now, where would my x-intercept be? Negative 1/3, comma 0, and 1, comma 0. Okay. Now, your y-intercept, guys, your y-intercept, you can find all that information from either one of these formats. Okay. I like to think about it this way. If I had a polynomial, what term is always your y-intercept for a polynomial? Constant, right? It's a non-variable term because my y-intercept is always when x is what number? 0. So it's just a constant term. So if x was 0 here and there, doesn't those two terms go to 0? You're left with just negative 1. So that would be the y-intercept of just that numerator. Y-intercept of the denominator, same concept, right? What's negative 1 divided by negative 2? 1/2. So my y-intercept is x is 0. Y is 1/2. Okay? You can gain the same thing from coming up to the factor form and say, okay, x has got to be 0. So I get 0 plus 1. I get 0 minus 1 when I substitute. I get 0 plus 2 and 0 minus 1. Gives me -1 up top, gives me -2 on the bottom. Still 1/2, right? Isn't it much quicker, though, to look at the expanded version? All right. All right, so that information there is critical for us to grasp, okay? I'm going to do this on GeoGebra just because it's so much cleaner. It'll be kind of a pain in the butt jumping back and forth. Let's see if I can just... That might not be too bad. So this is what you would do. You would do the exact same thing on paper, on a grid. If I gave it to you on Tester Quiz to graph one of these, you're going to graph your vertical axis. You got one at x equals -2. We got one at x equals, was it 1? 1/2? Okay. Now I'm going to just, so we can talk about them a little bit easier, visualize them a little bit easier, color them. Usually when you're graphing them by hand, you make them dotted so that you don't make the misinterpretation that they are parts of your curve, but they guide our curve. Does that make sense? Okay. And now our horizontal aspect was at 3/2. So that's a y equals 3/2. Okay. So what that does, guys, is it takes our, just zoom in on this real quick, that takes our coordinate plane, and did it break it up into 6 regions? Okay. Our graph is going to exist in some of those 6 regions. We just have to figure out which one. Okay. And I don't want to make any kind of blatant arguments that, you know, it's always going to happen in one of these 2. Okay. It might happen in one or both of these, and then it's going to happen in one of these 2. That's kind of common with a lot of the examples we see. But I don't want to make that argument right now, just because it's not a all-encompassing argument. Okay, but you will see a lot of similar behaviors as we graph these. All right, so I'm going to put in the point 4, 13, comma 3/2. That's where I cross my horizontal asymptote here at A. I'm going to put in my x-intercept of -1/3, comma 0, and 1, comma 0. I'm going to plug in my y-intercept of 0, 1/2. And now we're going to talk about what should happen here when we start filling in our graph. Okay? We understand, hopefully we understand the concept that our horizontal asymptote tells us in behaviors. Okay? We've got the algebraic work to show us how many times we cross our horizontal asymptote. We only cross it 1 time, right? Vertical asymptotes, if we go back to the definition of a vertical asymptote and find it, we talked about this last week. Okay, I know it's zoomed out real far, but this says the line x equals a is a vertical asymptote of the function y equals f of x if y approaches positive or negative infinity as x approaches a. Okay, so what that means to me, as I am approaching these red lines from the left to right, my graph is either going to go up to positive infinity or it's going to go down to negative infinity. That's my only 2 options. Does that make sense? Okay. Now, understanding that, in connection with what we've already got with the kind of critical data points here that we developed through the algebra, we should have a pretty good understanding of what our graph is going to do. Okay. I'm going to look just in this middle region right now. Okay. Because of how we understand graphing points, consecutive points, it makes sense that B, D, and A are going to end up being connected, right? Okay. We start finding more values, more ordered pairs in between B, D, and A. We're going to see if there's a smooth curve there. Okay. Now, A is where I cross my horizontal asymptote, right? How many times do you cross it? One time, right? Okay. And there was no math or anything like that that maybe showed me that I bumped it and went back down or anything like that. There's no multiplicity there, anything weird. I'm going to cross it. And now if I cross it, I get kind of that little black segment just as I move to the right. What are my only options? What is the only thing I can do now as I get closer and closer to that red dotted line? I can only shoot up, right? I can't come back down because if I was able to come back down, I would have crossed the asymptote again, right? And then I would have had algebra that supported that. I don't have algebra that supports me crossing the asymptote twice. So then move to the right. I'm going to go to positive infinity, get sucked towards that asymptote. I'm going to touch it, and we suck close to it. Okay? Now think about this. Let's go from B. We went from B to the right. Let's go B to the left now. As I go to the left, okay, am I ever going to come back up over the x-axis? No, I don't have any more x-intercepts over there, right? Okay. I'm not going to cross for the same reason, ultimately the same reason I don't have any math that supports that would cross this asymptote again here, the horizontal one. So as B goes, as we move points from, what was that, -1/3, and move left, I'm going to get a graph that kind of does that. Does that make sense? Okay. Now let's go to the right of that asymptote here that's at 1/2. I get this intercept here at C. Okay. Will I ever go above that blue line again? No. Will I ever go to the left of that vertical line through 1/2? No. Okay. So there's always two things I can do from C in both directions. I can either go up or I can go down, right? Which one do I have to do here? So right here, don't I have to go up? Doesn't my horizontal asymptote tell me in behavior? So as x goes to the right, that green curve needs to get sucked up to it. Okay, because it's going to show me that when x is out to 400, 400 million, 400 billion, my y value is going to be very, very close to 0.75. Okay? Or not 1.5, I think it was 3/2. Now, as I move to the left of C, can I go back up? No, because I don't cross the asymptote again, right? So my only option is to go down. Okay? So that took care of all that difference. And this is going to be, it has to be a function, right? It has to pass the what to be a function? Vertical line test. So can I have anything up here? No. Okay? I could have some stuff over here. So I got to check over here. This is where I had down there at the bottom said T-chart if necessary. It's necessary. I need to figure out a point or a series of points for the left of -2. So I'm just trying -3. I plug -3 in. Okay? So I don't know what my original function was. Give me the factor form. The 3x minus 1. On here. All right, so I would plug in negative, because I want to do a T-chart, right? I would plug in a value to the left of -2 into that thing right there. I'll plug in -3. If I plug in -3, it's going to give me -8 times -4, which is 32, right? Plug in -3 here, it gives me -1 and -7. So it gives me +7. Make sense? So 32/7. I'll go -3, -3, comma, 32/7. And we'll get that point right there. So does it make sense then as I go to the right? The graph is going to do that. As I go to the left, I'm going to get sucked down to that horizontal asymptote. So once I do that, the next thing I would do, guys, is go back and I would type in the original P of x, or R of x, original function. And it's going to graph on top of what we just did by hand. Okay? I'm going to post the homework assignment, not due tomorrow. And then at some point today, I'll send out an email with your practice testing. I will pick up with more examples tomorrow.
I'm gonna have to dig it out. Hold on a second.